Unit 3 Practice Exam Version B. Here we go. This question 1 is from section 2.1, Graph an exponential function. So what I would suggest doing first is locating the horizontal asymptote. So you can find that with this transformation that occurs outside the function, plus 1. It means the horizontal asymptote is up 1 unit. And then we need to find the y-intercept by plugging in a 0 for x. 2 to the 0 power is 1. 1 plus 1 is 2. So 0, 2. And then the last thing you need to do is just plot some additional points. So I'm going to let x equal 1. 2 to the first power is 2. 2 plus 1 is 3. And then when x equals 2, 2 squared is 4. 4 plus 1 is 5. Okay. It says state the domain and range. So the domain, this graph extends from negative infinity to positive infinity. So the domain is going to be negative infinity to positive infinity. The range on the y-axis here, this graph does not go below the horizontal asymptote. So the horizontal asymptote occurs at y equals 1. This graph never reaches y equals 1. It stays just above it. So the range would be parenthesis, not a bracket, parenthesis, 1 to infinity. Okay. We plotted several points. Now it just wants to give an equation of the horizontal asymptote. That's y equals 1. Okay. Graphing logarithmic functions is from section 2.3. Logarithmic functions have a vertical asymptote. Usually it's here on the y-axis, unless there's been a horizontal transformation, which there has because this occurs inside the function. So remember, x plus 1 moves to the left 1 unit. So the vertical asymptote is to the left 1 unit. It says give an equation, so that's x equals negative 1. Now we need to find the x-intercept that occurs when y is equal to 0. So plug a 0 in for y right here. That's going to be the equation 0 equals log base 2 of x plus 1. In order to solve this, we need to cancel the logarithm, so I'm going to use a base of 2 on both sides. So base of 2 here and here. Base 2 is going to cancel the logarithm. So that's going to leave us with 2 to the 0 power here is 1. So this is 1 equals x plus 1. Subtract 1 on both sides and we get x equals 0. Now what we talked about in section 2.3, to get other points on the graph, you could continue to plug values in for y, or you could plug values in for x. Either way, since we have a log base 2, you're going to want to make sure that whatever this turns out to be is a power of 2. For example, if you plug in x equals 1, 1 plus 1 is 2. So x equals 1 would be a pretty good value to choose. 1 plus 1 is 2. Log base 2 of 2 is equal to 1. And then the next power of 2 is 4. So we would want this to turn out to be 4. So we're going to let x equal 3. 3 plus 1 is 4. Log base 2 of 4 is equal to 2. Okay, domain. On the x-axis, the graph does not go any less than, or the x values do not go any less than negative 1, and they never actually reach negative 1. It just stays barely to the right of that vertical asymptote. So the domain we're going to say is from -1 to infinity, but not including -1. That's why I use a parenthesis here. The range goes all the way down from -infinity to +infinity. Okay, question 3 is partly from 4.3. This one's from 4.2, where you have to combine two logarithms first. So it's a combination of 4.4 and 4.3. So first, we're going to take two logarithms and condense them into one. Now, because there's a minus sign between them, we're going to use the quotient property, or the quotient rule. So we're going to make 1 log base 6 of 72 divided by 2. So this is log base 6 of 36. And that's log base 6 of 6 squared. Those cancel. And we get 2. Now, excuse me, for part B, e as a base will cancel natural log as an exponent, but we have to do something with this 2 that's in front of the natural log before they can cancel out. So remember, any value that's in front of a logarithm was at one point an exponent. That's the power rule. So we're going to move this 2 here back up as an exponent on the 4. So we have e, and then the exponent is natural log of 4 squared. Now that there is no value in front of the natural log, and it's an exponent with a base e, those are going to cancel each other out. So that leaves 4 squared, which is 16. For part C, we need to change the 1/9 into a base of 3. And it's 3 to the power of -2. Right here, 3 to the power of -2 is the same thing as 1/9. Now that they have matching base, they're going to cancel out. And the answer is -2. Question 4 is from 4.4, more of those rules and properties of exponents, or logarithms rather. So you may recall I've said this a couple times. Radical signs like square roots and logarithms don't match too well. So you're always going to want to change these radicals into a rational exponent. So a square root is the same as a power of 1/2, or an exponent of 1/2. So this would be x squared times y to a power of 1/2. Now, this power here can move down in front of the logarithm because of the power property. So I'm going to take this exponent of 1/2 and move it down in front of the logarithm. So this is 1/2 times the log base 3 of x squared times y. Now here we're going to expand this logarithm into 2 because we have a product, x squared times y is a product. So we're going to expand the logarithm. And one thing to keep in mind, this is a common mistake, this 1/2 that's in front of the single logarithm needs to be a coefficient in front of both logarithms when you expand it. So the way you can do that is put a parenthesis there. So this is log base 3 of x squared plus log base 3 of y. Now you'll be sure to distribute the 1/2. So I'm going to go ahead and distribute this 1/2. So this is 1/2 log base 3 of x squared plus 1/2 log base 3 of y. Now the final step is to take this exponent of 2, move it in front of this logarithm, and it's going to multiply with 1/2. 1/2 times 2 is 1. So final answer is log base 3 of x plus 1/2 log base 3 of y. Okay, question number 5. We are going to invest $8,000. We want it to double. What would the interest rate need to be if it compounds continuously? So this is an important phrase right here, compound continuously. That means we're going to use that finance formula, where this is the future amount, this is the principal investment, interest rate is R, time is T. And I said, what would the interest rate need to be? So we're solving for the interest rate R, which means we need to have a value for time, we need to have a principal investment, and we have to have a future amount. So the principal investment is $8,000, and we want it to double, so that $8,000 is going to become $16,000, and it needs to double in 25 years, so that's going to be our time value, and then we're going to solve for R. So the future amount, 16,000, is equal to the initial investment of 8,000 times E, and then the exponent, we're going to leave R because we don't know the rate, that's what we're solving for. And time is 25. So we need to get base E by itself because this is what we need to solve for R, and we can't solve for R if it's an exponent, so we need to cancel the base. We can't cancel the base until the coefficient is gone, so divide by 8,000, we're going to get 2 equals E to the 25 times R. Now we can cancel the base E using natural log on both sides. So that's the natural log of 2. Remember, the natural log and the E cancel each other out. So this is 25R divided by 25. So the interest rate is natural log of 2 divided by 25. And that's approximately 0.028. So the interest rate is about 2.8%. Okay, question 6. This is from section 4.5, solving exponential equations. So the thing that has to happen to solve an exponential equation is to get the term that has the base and the exponent. The exponential term needs to be all by itself. So there's a -1 we need to get rid of, and there's this coefficient of 2 that we need to get rid of. Remember, you cannot combine the 2 multiplied by 4 to make that 8. That doesn't work. You're going to have to divide the 2 over. So first step is add 1. So we have 2 times 4 to the x minus 1 equal to 16. Then divide by 2. And we get 4 to the x minus 1 is equal to 8. Now we want to cancel the base 4, so we're going to use log base 4 to cancel the base 4. So what we have is now the x minus 1 is no longer an exponent. It's just an expression with no base of 4 because it was canceled by the logarithm. So on the left side we have x minus 1, on the right side we have the log base 4 of 8. Now we will solve for x by adding 1. It cancels there, so the exact value is x equals log base 4 of 8 plus 1. So it wants both the exact and the approximate. So there's the exact form. The approximate solution is first using the change of base. So this is log 8 divided by log 4 plus 1. And that's, well, not approximately, it's exactly 2.5. Okay, part B, we need to get e to the x plus 2. We need to get this term all by itself so that we can use natural log. So we need to get rid of the plus 4 and then get rid of the 3. So first step is to subtract 4. So that's 3 times base e to x plus 2 equals 9. Now divide by 3. And we get e to the power of x plus 2 is equal to 3. Now to cancel the base e, use natural log. So then the base e is gone, so the x plus 2 is no longer an exponent, it's just an expression of x plus 2, so x plus 2 on the left, and then on the right we have equals natural log of 3. Now we can subtract 2. And we have x is equal to the natural log of 3 minus 2. That's our exact form of the answer. And then the approximate form is negative 0.90. Question 7 is also from section 4.5, solving a logarithmic equation. Now, to cancel a logarithm, remember we have to use a base, so we're going to use a base of 2. But before we use a base of 2 to cancel a logarithm, this should be the only term on that side of the equation, so we need to subtract a 3. We have log base 2 of x minus 1 is equal to 2. Now we cancel a logarithm using a base of 2. So we have now x minus 1 is equal to 2 squared, which is 4. Add 1 to both sides. And we get x is equal to 5. That's always a good idea with logarithmic equations to check your solutions, because remember with logarithmic equations, the domain is restricted. You can't have values inside of a logarithm that make negative values. So if you plug in a 5 here, 5 minus 1 is 4, so that's fine. And the log base 2 of 4 is 2. 2 plus 3 is 5. Very easy to check most of the time your solutions with logarithmic equations. For part B, the problem here is you cannot solve a logarithmic equation if there's 2 logarithms on the same side of the equation. You can have one logarithm over here and another logarithm on the other side of the equation. You just cannot have 2 logarithms on the same side. So what we did is condensed the logarithms into one. Since there's a plus sign between them, we're going to use the product property. So 2x and x minus 5 are going to form a product within a single logarithm. Now that we have one single logarithm on the left side, we can cancel it using a base. And because it's a log base 10, we're going to use base 10. So base 10 cancels that logarithm. So now we have two x times x minus 5 is equal to 100. We distribute there. We have 2x squared minus 10 is equal to, minus 10x rather, is equal to 100. So subtract the 100, we get 2x squared minus 10x minus 100 is equal to 0. This is just a quadratic equation. I'm going to go ahead and factor out a 2. And then that factors into x minus 10 and x plus 5. So then two potential solutions we get out of that are x equals 10 and x equals negative 5. Now remember, with logarithms, you should check negative 5 right here. 2 times negative 5 makes negative 10. You can't have negative 10 inside of a logarithm. So negative 5 doesn't work. Check the 10 also. 2 times 10 is 20. That's fine. 10 minus 5 is 5. That's fine also. So 10 works. If you don't cross out any solutions that don't work, those are called extraneous solutions. If you don't cross them out on the exam, then you won't be able to get full points for the problem. Okay, question 8. This is from section 4.6. We need to find a function that models the amount remaining and then use that model to find the remaining amount after 175 years. So we have a radioactive isotope that has a half-life. Because there's a specific half-life mentioned, I'm going to use the half-life model. Which is the amount at any time t is equal to the initial amount and a base of 1/2. The exponent is t over x. And remember, x is your half-life time, which in this case is 432.2 years. A sub 0 is your initial amount, which is 10 grams. So the half-life model we're going to use is the amount at any time t is equal to our initial amount, 10 grams, base of 1/2, with an exponent of t over 432.2. And you have to make sure now that the given half-life unit of measure is the same as what you're trying to find, years and years. And that same thing goes for a doubling time model, because sometimes I'll try to trick you and mix units of measure with time, so make sure these match, and they do. So there's the model we're going to use. Now they want us to answer how much of the 10 gram remains after 175 years. So that 175 years is just the value of time that goes right here. So the amount after 175 years is going to be found using this. So this is a calculator problem. And there's going to be 7.55 grams remaining. Okay, question number 9, also from section 4.6. We have a population of trout, and this is the number of trout at any given time. How long will it take for the population to reach 8,000? So the population is given by this variable here, p of t. So how long will it take is the measurement of time. So we're solving for t, which means the 8,000 population goes right here for the population. So we're solving 8,000 equals 10,000. And we're solving for t. Now, we do not like solving equations that have fractions. So one thing we can do is multiply both sides by the common denominator. So that'll cancel it there. So on the left side we have 8,000 multiplied by this denominator. So a couple things you could do here. You could distribute the 8,000 into the parenthesis, or because it's multiplying here, you could divide. I'm going to divide by 8,000. We have 1 plus 19 times the base e to the negative 1.56t. So 10,000 divided by 8,000 is 5/4. Now we subtract 1. 5/4 minus 1 is 1/4. So this is 19e negative 1.56t equals 1/4. Now divide by 19. So this is e to negative 1.56t is equal to, this is 1/76. Now to cancel the base e, you can use natural log. So now we divide by negative 1.56. And t is equal to the natural log of 176 divided by negative 1.56, which is approximately 2.78 years. Now we get into questions from Chapter 8. You will have a formula sheet for formulas that you'll need to use in Chapter 8. Question number 10 is from Section 8.1. Find the first 4 terms of each sequence. This is an explicit formula, or an nth term. This part B, remember, is a recursive formula. But for both of them, you're just listing the first 4 terms. With an explicit formula, to list the first 4 terms, you plug in n equals 1 for the first term, n equals 2 for the second term, and so on and so on. So for the first term, if we plug in n equals 1, 2 to the first power is 2. 2 divided by 2 is 1, so the first term is 1. To find the second term, we plug in a 2 for n. 2 squared is 4. 2 divided by 4 is 1/2. To find the third term, we plug in n equals 3. 2 to the third power is 8. 2 divided by 8 is 1/4. To find the fourth term, we plug in a 4. 2 to the fourth power is 16. 2 over 16 is 1/8. Now our recursive formula that we talked about in section 8.1 is a little different. It gives us the first term, which is negative 3. So we know the first term is negative 3. And then this describes how to find the next term. So a sub n, which we could think of as the next term here, if this is a sub n, then a sub n minus 1 is the term in front of it. So a sub n, which is this term, is equal to a sub n minus 1, subtract 2. So we're going to subtract, to find this term, we subtract 2 from this term. So negative 2 minus 2 is negative 5. Now the next term is a sub n. So if this is a sub n, then this is a sub n minus 1. So to find this term, we subtract 2 from that term. So that's negative 7. Now to find this term a sub n, we go to the term in front of it, a sub n minus 1 and subtract 2. Pretty much we're just subtracting 2 every time. So question 11, it isn't clear which section this comes from. Explicit formula, we practiced finding the nth term or explicit formula for an arithmetic and a geometric, so we need to figure out which one this is. So if it's arithmetic, there's a certain way to do it. If it's geometric, there's a different way of doing it. So from -4 to 2, then from 2 to 8, and from 8 to 16, there's a consistent increase of 6, a common difference. So common difference is 6. That means this is arithmetic. So the nth term is going to be linear with a common difference acting like the slope. And then there's a couple ways you could do this. This term that follows here, if this is linear, then if this is your slope, then this term would be your y-intercept. That occurs when x equals 0. Well, there is no term when n equals 0. This is when n equals 1. But if there were a term in front of the first term, it would be -10. Or there will be a formula given on the formula sheet. It's the nth term of an arithmetic sequence. It looks like this, a sub 1 plus n minus 1 times d. So the first term is -4, and the common difference is 6. So if you distribute, you're going to get -4 plus 6n minus 6. Combine the -4 and the -6 to get -10. Question 12 specifies that this is arithmetic. That's important because that means the nth term is going to be linear. If it's linear, it has a common difference or a slope. So we're going to find the common difference much like we would find the slope of a linear function. So this is an x value and this is a y value if we want to think functions. So the common difference is the difference in y values, or these values here, so that'd be 86 minus 47, divided by the difference in x values, which would be these values here, 24 minus 11. So 86 minus 47 is 39. 24 minus 11 is 13. So the common difference is 3. So we could actually use this formula because we know the common difference. We don't know the first term, but we know, for example, that the 11th term when n equals 11 is 47. So we could plug a 47 in here and an 11 here and a common difference of 3 to solve for that first term. That's one way we could do this. So we're going to use, like I said, we're going to use this. This will be a sub n, and then we'll do n equals 11. And plug that in here and a common difference of 3. So 47 is equal to the first term, which we don't know, and then 11 for n, and then a common difference of 3. 11 minus 1 is 10. 10 times 3 is 30. Subtract 30 from 47, and you get 17. And then we could use this formula again. Now that we know the first term is 17, we could say a sub n equals 17 times n minus 1 times d. Distribute the 3. Seventeen minus 3 is 14, so the explicit formula is 3n plus 14. Okay, question 13. Again, it's not clear what section this comes from at this point because it just says partial sum. Remember, we did partial sum of arithmetic and we did a partial sum of a geometric, so we need to determine what kind of sequence this is. From 17 to 24 is an increase of 7. 24 to 31 is an increase of 7. 31 to 38, so they're all increasing by 7. So there's a common difference, which means this is arithmetic. So the partial sum formula for arithmetic is first term plus last term multiplied by n over 2, where n is the number of terms being added. We do not know how many terms are being added. It's not clear if 185 is the 10th term or the 15th. What we need is the explicit formula. So we know the common difference is 7. So we know that a sub n is equal to 7n. If there were a term in front of the first term here, it would be 10. So it's 7n plus 10. Now, for this value, 185, that's an a sub n value. What we don't know is the n value. We don't know which spot in the sequence is it. So this 185 can go right here for a sub n. And we can solve for n. Subtract 10 and divide by 7. So 175 divided by 7 is 25, so n equals 25. That means this is the 25th term in the sequence, so we're adding 25 total terms. So n would be 25, the first term is 17, the last term is 185. So the sum is first term plus last term multiplied by 25 over 2. So 185 plus 17 is 202. And if we multiply 202 times 25 halves, we get 2,525. For part B, again, it's just to find the partial sum, so you have to determine which partial sum formula is appropriate, and when it's in sigma notation, you look at the explicit formula. 2n plus 6 is linear, which means this is arithmetic. So you're going to use the partial sum formula of an arithmetic sequence. Now we know how many terms we're adding together. We're adding 17 terms. What isn't clear is what's the first term and what's the 17th term. We can find that by plugging a 1 in for n. And then to find the 17th term, just plug in a 17. So the first term, a sub 1, if we plug in a 1 for n, 2 times 1 is 2, 2 plus 6 is 8. To find the 17th term, we plug in a 17. 2 times 17 is 34. 34 plus 6 is 40. Okay, so now the sum is the first term plus the last term multiplied by half of the number of terms we're adding. So this is 48 times 17 halves. And this is 408. Question 14, find the nth term. So again, it could either be in arithmetic or geometric. So if we look at 2 to 4/3 to 8/9 to 16/27, it doesn't look like we're adding the same value. But if we go 2 to 4/3, that's multiplying by 2/3. If we multiply by another 2/3, we get 8/9. If we multiply by another 2/3, we get 16/27. So it's a common ratio this time of 2/3, which makes this a geometric. So this is a geometric sequence. The nth term or explicit formula that you'll find on the formula sheet is a sub n equals a sub 1 times the common ratio to the power of n minus 1. So first term is 2, the common ratio is 2/3, and the exponent is n minus 1. Okay, for number 15, evaluate the sum of the following geometric. So this one is pretty clear, it's geometric. So the partial sum of a geometric you'll find on the formula sheet. So what we need to know is what's the common ratio, how many terms are we adding, and what's the first term? Well, the first term is 2. To go from 2 to 16, or from 2 to 6 rather, and from 6 to 18, 18 to 54, looks like we're multiplying by 3, so the common ratio is 3. But what we don't know is how many terms are we adding together. 118,098. We need to figure out which term that is. So we could use the explicit formula for this, which is a sub n equals first term times the base 3 to the power of n minus 1. This is an a sub n value, but we don't know its n value, so we could solve for it. We could solve for n by plugging 118,000 in for a sub n. Now the variable we're solving for is an exponent, which makes this an exponential equation, so we have to solve this using logarithms. We're going to divide by 2. So now there's no 2 coefficient. So 118,098 divided by 2 is 59,049. Now to cancel a base 3, we have to use a log base 3. Log base 3 is going to cancel that. So we have log base 3 of 59,049 equals n minus 1. Now if we do change the base here, this is log 59,049 divided by log 3 equals n minus 1.
Thank you.
And this turns out to be 10. If you add 1 to both sides, you get n equals 11. So this is the 11th term. So 11 is what we plug in for n. 3's are, a sub 1 is 2. So the sum is 2 times 1 minus 3 to the 11th power times 1 minus 3. And from that we get 177,146. For part B, this is sigma notation. It's a partial sum because we're only adding 7 terms. So you have to decide which partial sum formula. And again, you decide by looking at what kind of function this is. This is exponential, which means this is geometric. So we're going to use the same partial sum of a geometric sequence. So the common ratio R is given here. First term a sub 1 is given here. And then n is the number of terms we're adding together, which is given there. So a sub 1 is 3, R is 1/2. The number of terms we're adding together is 7, so those just get plugged in to the formula. 3 times 1 minus 1/2 to the 7th power divided by 1 minus 1/2. And that comes out to be 5.95. Okay, part C. Infinite sum only works. Remember, there are two things that have to be true in order for an infinite sum to be possible. Number one, it has to be a geometric series. This is, because this is an exponential function, so it's geometric. The second thing, it has to have a common ratio less than 1. So 2/3 is the common ratio. It's less than 1. So R is equal to 2/3, and the first term is equal to 2. So the formula for the infinite sum is first term divided by 1 minus R. So this is 2 divided by 1 minus 2/3. So that's 2 divided by 1/3, which is 6. Now question 16 is from section 8.6. We need to expand using, I'm going to use Pascal's triangle. So if the exponent is 4, we need the fifth row of Pascal's triangle to get the coefficients for the expansion. So there's row 3, there's row 4, and there's row 5. So these are the coefficients. So we're going to start with the first coefficient, 1, and then we have 3x to the fourth power. And we still have the other term, 2y, but it's to the 0 power, which means it's just 1. And then the next term has this as a coefficient, 4, and then the 3x decreases to a power of 3, and now the 2y increases to a power of 1. And then we use a 6th coefficient. The 3x decreases to a power of 2, the 2y increases to a power of 2. And we use a coefficient of 4. The 3x decreases to a power of 1, the 2y increases to a power of 3. And finally we have a coefficient of 1. The 3x decreases to a power of 0, which means it's just 1, and the 2y increases to a power of 4. And now we simplify the expressions. 3x to the fourth power is 3x times 3x times 3x times 3x, and then times 1. 3 to the fourth power is 81, so that's 81 times x to the fourth. Now here we have 3x to the third power, so that's 3x times 3x times 3x, which is 27x cubed. So we have 4 times 27x cubed times 2y. And then 3x to the second power is 9x squared, so that's 6 times 9x squared times 2y to the second power is 4y squared. And we have 3x to the first power is just 3x. 2y to the third power is 8y cubed. And then 2y to the fourth power is 16 y to the fourth. And then we continue to simplify here. 4 times 27 times 2 is 216. And 6 times 9 times 4 is also 216. 4 times 3 times 8 is 96. And then we have 16 y to the fourth.